Hello viewers, in today's class we are going to discuss yet another important and conceptual problem from definite integrals involving greatest integer function, right? So here we have this problem and we have to integrate the greatest integer of 1 plus square root of 3 tan x from 0 to pi by 6, right? So here our integrand involves the greatest integer function. So let us solve this integral. Now we'll solve this integral by the method of substitution, right? We may also use the method of inequalities, but here we will prefer the method of substitution, right? So let us first take this integral as I, and let us first substitute y is equal to 1 plus square root of 3 tan x, right? Okay, so now we have y is equal to 1 plus square root of 3 tan x, and let us differentiate both sides with respect to x, right? So we have dy over dx is equal to square root of 3 secant square x. So the derivative of 1 is 0 and the derivative of tan x is secant square x. Now here we'll make use of one important identity, that is 1 plus tan square theta is equal to secant square theta, right? So now we have dy over dx is equal to square root of 3 and we have 1 plus tan square x, right? For sec square x we can write 1 plus tan square x, right? And for tan x we can write the value of tan x in terms of y as tan x is equal to y minus 1 over square root of 3, right? So we'll take this value over here. So we have root 3 and we have 1 plus y minus 1 over root 3 square, right? Now we can simplify it. So we have square root of 3, then we have y minus 1 whole square is equal to y square plus 1, then we have minus 2y over 3, right? So let us simplify it further. We have 3 plus y square plus 1 minus 2y over 3, and we can write it like this. So we have root 3 over 3 and we have y square minus 2y plus 4, right? Now rationalizing the numerator and denominator by root 3, we have 3 over 3 root 3 and y square minus 2y plus 4. So root 3, here 3 and 3 get cancelled. We have y square minus 2y plus 4 over root 3, right? So now we can write dx as root 3 over y square minus 2y plus 4 dy, right? So we have the expression for dx in terms of y. Okay, so now let us change the limits accordingly. So here we see that x varies from 0 to pi by 6, right? So when x is equal to 0, we can calculate the value of y from this expression. So we have y is equal to 1 plus root 3 times tan of 0. So we have 1 because tan 0 is equal to 0, right? And when x is equal to pi by 6, we have y is equal to 1 plus root 3 times tan pi by 6. So we have 1 plus root 3 times tan pi by 6 is equal to 1 over root 3. So here we have 1 plus 1, that is 2, right? So when x varies from 0 to pi by 6, y varies from 1 to 2, right? So now this integral I can be written as integral from y is equal to 1 to 2 greatest integer of y, because for 1 plus root 3 tan x we can write y, and for dx we can write root 3 over y square minus 2y plus 4 dy, right? Now taking root 3 outside the integral, we have 1 to 2 greatest integer of y over y square minus 2y plus 4 dy, right? So now here we have I, and now see the value of y varies from 1 to 2, right? That is, y lies between 1 and 2. So when y lies between 1 and 2, then obviously the value of greatest integer of y is equal to 1, right? So here we'll take 1. So this integral I, it reduces to root 3, 1 to 2, and here we have 1 over y square minus 2y plus 4 dy, right? Now see, this integral reduces to this form, that is dx over ax square plus bx plus c, right? So in the denominator we have a quadratic polynomial. So when we have the integrand in which the denominator is a quadratic polynomial, what we do, we express this quadratic polynomial as a sum of a perfect square and some number, right? So we can write it as root 3 1 to 2, and we have dy over y square minus 2y plus 4 can be written as y square minus 2y plus 1, and here we can write 3, right? So now this expression is equivalent to y minus 1 square, right? So here we have 1, here we have 2, then we have dy, and this is y minus 1 square plus 3, right? And 3 can be written as root 3 square. Now let us again make use of the method of substitution here. So what we will do, we'll take t is equal to y minus 1, right? So when t is equal to y minus 1, dt is equal to dy, and see, y is when y is 1, t is equal to 1 minus 1, that is 0, and when y is equal to 2, then t is equal to 2 minus 1, that is 1, right? So now this integral I, it becomes square root of 3, and we have the limits from 0 to 1, right? From 0 to 1, and for dy we have dt, and in the denominator we have t square plus root 3 square, right? Now in order to evaluate this integral, we'll make use of this important result from indefinite integrals, that is dx over x square plus a square is equal to 1 over a tan inverse x over a, right? So we'll make use of this result to evaluate this integral. So here for x we have t, and for a we have square root of 3, right? So we have I is equal to root 3 times 1 over a. So we have 1 over root 3, then we have tan inverse and x over a, that is t over square root of 3, and the limits are from 0 to 1. So root 3 and root 3 get cancelled, and we have tan inverse t over root 3, and the limits are from 0 to 1, and when t is 1 we have tan inverse 1 over root 3, and when t is equal to 0 we have tan inverse of 0 over root 3, right? So tan inverse 1 over root 3 is simply pi over 6, and tan inverse 0 is equal to 0, so we have pi over 6, right? So the value of this integral is equal to pi over 6. So this is how we can solve this type of integrals.